Good morning. My name is Catherine Ramsdale. I work at PragmatIC. You are going to hear a very similar message from me as you just heard from Chris. We are working on the commercialization of flexible electronics into manufacturing. And my talk will go through roughly what we're doing in that arena. Okay, so in brief, what I'll discuss is I'll introduce PragmatIC for those of you who don't know who we are, and then go through the motivation for the work that we're doing, how we go about it, and how similar or different that is to silicon, and then how we're proposing to implement it, and the general parts of the ecosystem that need to be in place to do that. So PragmatIC is a company that has been around about 6 or 7 years, and we are working on flexible integrated circuits to enable the trillions of smart objects you've heard mentioned elsewhere in the conference. We're about 50 to 60 people in size. About half of them are in Cambridge, looking at design aspects, application aspects, and test, marketing, business development. And then in Sedgefield, in the Centre for Process Innovation, we've embedded about 25 staff there. And that's the centre, a catapult centre owned by the government, and that gives access to a lot of CapEx equipment that you don't have to buy yourself. You can go and use their facilities, and you can use that to develop your processes to show that you are able to do kind of pilot level production before then getting investment to do your own production. So we have had investment from a range of different investment arms, including some from Arm and Avery Dennison at kind of either end of our space. And then the other companies on there show the kind of organisations we've worked with in projects to develop the technology that it's. So why would we do this? This is the cost slide and where we fit relative to silicon. So in your computer, an IC in your computer is roughly on the cost of $100, and those ICs, about 300 million ICs are sold per year. If you get the cost down to $1 to $10 for the kind of IC that is in your smartphone, then your volume of sales goes up to about 50 billion units per annum. But if you can get your cost down into the cent or sub-cent level, then suddenly a whole new world opens up for you, and you can look at trillions. Now, that sounds like a big number, but if you think about how many computers you bought in the last year, and then think about how many phones or other connected devices you bought in the last year, and then think about how many things you bought in Tesco's or had them delivered last week, you can see that that is not an impossible number, even in your own weekly shop. So if you can get your cost down to the point where you wouldn't notice it on a packet of cereal or a carton of milk, then you can imagine that you could tag everything, and systems such as checkout free, leaving your shop and that kind of thing become much closer to reality. So that's the market we're looking at. We are not looking at smartphones, and we are not looking at computers. That is where silicon excels, but there is no way currently that silicon is going to get down to the cent or sub-cent cost for IC. And we do not need that level of complexity for these products. They're intelligent, but they're not super intelligent. So here are the kind of the building blocks that you additionally need or might need if you're looking at smart packaging. So you might need some kind of sensor. As Chris said, you might have a label on a wine bottle that tells you what the temperature of your wine is. You might need something in your in a birthday card that knows when you've opened it, some kind of light sensor. So there are those kind of applications required. You need some kind of energy source. Batteries are expensive, even flexible batteries. So NFC is preferred, or some kind of wireless harvesting. And then some circuitry, so to do whatever your logic is, make it flashlights, make sounds, RFID, and then potentially some kind of display if, for example, you want to make lights flash on beer bottles, which is a surprisingly robust area that people are interested in doing, then that kind of thing comes up, and you need to have the display as well. So our area is in the circuit, and then obviously we take the other parts from other businesses. So that's the novel part of our technology, but we only want to be novel where we need to be novel. There is no point reinventing the wheels that silicon has already invented many years ago. So we need to be developing our technology in a way that would match with the standard flows with silicon as far as it is possible to do so. Of course, it's much less mature, so which one's the pointer? This one. It's much less mature, so this is actually a realistic iterative loop. So you need to model your transistors, and you need to then design your circuit with those transistors, and then you need to make it. And then when you don't quite get out what you expected, you need to go back round that loop again. Now, in silicon nowadays, your mask sets are incredibly expensive. That would cost you quite a lot of money to basically just try it, see what you get, and start again. But our mask set costs are orders of magnitude, many orders of magnitude cheaper than silicon mask set costs. And so this becomes a realistic loop for the quickest way to work out how to make your device or how to make your circuit and how to make it repeatable. So we follow the same, very similar methodology. We have a design rule manual where we describe each of the layers in our circuit, and we end up with something that is for the transistor, which is shown here, which uses all the different layers that are in the TFT, and then we make it. And then we see how what we made looked compared to what we intended to make, and we refine our design rules as we find out more about our circuit. So in that respect, that's very similar to silicon, but there isn't a basis for this, so we have to start it ourselves from the ground up. Then you need a SPICE model. So we have baseline wafers that we make on a weekly basis at CPI. This is a graph showing kind of one of the KPIs we measure, which is on voltage, and the distribution of on voltage as a function of voltage. And then from that, we can pick where our typical transistor is and use that to simulate the same transistor performance. We have models where we can scale that with width and length, and the same as silicon. And we have a slow case and a fast case, again, similar to what you'd have in silicon, so that we can have corner simulations and model our circuits with respect to the corners. However, as Chris pointed out as well, the models available for the technologies that we're looking at are not derived from the technologies we're looking at. We have to use silicon-based models to model our transistors. So, as an example, if you take temperature, in crystalline silicon, as you heat your transistors up, their performance goes down. They become more resistive. In this technology, if you heat your transistors up, they become less resistive. So you have to be very careful where you're going to use your model to make sure that it describes well enough your technology. And if you change something, like the temperature, you need to do it all again, or you need to at least find how you're going to manipulate the model so it gives you the right answer, which is not the same as the right answer in silicon. So it's the genuine thing from the previous slide where you do have to do this iteration, because you cannot assume that the model is accurately predicting what your device will do over a different range of parameters. So we've worked very hard on this to get our performance and our uniform and the simulation to match the devices across a range of different corners. So this design flow would look very similar to a silicon version, just to show that we are working with a silicon mindset insofar as it's possible to do so. So we have schematics, we have simulation, we have layout, we use place and route, we have a design rule checker, we use LVS, and then we tape out. This bit, as I said, the cost of that is significantly lower than the cost as it would be in silicon, so we do this relatively frequently in order to refine our techniques and to refine the way that we are developing the technology. So once we've got the model and we've got the simulation and we've designed the circuit, again, in a similar way to as you would do in silicon, we make cell library of small building blocks of logic in order to assess whether it works as we expected it to based on the modeling. So this is an example of an 8-bit counter. The design is here, and then and the layout, and then we characterize the functionality of the counter and make sure it does what we're expecting it to do, and assess the timing parameters and those kind of things to better refine our models and our simulations in part of this iterative loop that I talked about. Once you've got that, you can move then on to circuits and building more complicated structures. So this is an RFID tag from some point last year that we designed, which had a 16-bit code generator within it. The layout was auto-generated with place and route software. And we simulated the expected output of the code generator, and then we measured the actual output of the code generator, and we ended up with the same answer. That then, of course, allows further refinement of an improvement of that when you can believe your simulations. So where are we in making this into manufacturing? As I said, our aim is to be able to produce these. So at the moment, we are housed in the National Centre for Printable Electronics in Sedgefield. It's a clean room, about class 100, I think, maybe class 1000 in some places. They have a large amount of off-the-shelf capital equipment that you can hire by the hour or by the day, and you can use that to validate your processes. And we have found that invaluable because it meant that we didn't have to make the capital investment ourselves at the point of which where we were showing individual numbers of transistors. You can get to the point where you can develop your circuit and your models are developed and your flow is developed before you really have to commit a capital amount yourself to your production flow. So that facility on its own, if we were to use that, would provide us with about 10 million Flex ICs per year, which is insufficient for almost any application product you can think of if your product line is, say, a shampoo bottle. That would not even cover the UK in the number of shampoo bottles required per year. So at the end of last year, we received investment for building our own dedicated facility. So that will still be in the same building, but it's our own dedicated facility. It's been called a fab in a box. It's fully integrated with modular equipment. It's all off-the-shelf equipment. Again, we are not looking to be novel in places we do not need to be novel. There's enough novelty in the technology without being novel in anything else. And that will be capable of a billion or so Flex ICs per modular line, and the cost will be in the very low cost cents range for a Flex IC. So where are we in doing that? This just gives you a flavour of the actual size and the space required compared to, say, Chris's picture of that display line that you saw, which was an aerial shot in order to fit the whole building in. Here, this is a picture with a camera of the kind of size we're talking about inside the facility, and here you can see the man and the whole line that will produce that kind of numbers. So we are talking about a much smaller capital investment, a much smaller area footprint-wise, and much smaller building investment for these facilities, which makes the entry level for anybody wanting to produce it significantly easier to cross that threshold, because the investment required is not in the billions of dollars. So a bit more on the production cost. Let me just get this one all the way up. So this, you've probably seen before, these kind of graphs where it's a cost versus silicon, and where the cost advantages come in. We've talked, and Chris also talked about these circuits being very low complexity. And there comes a point where this flat line is on these curves here, where you just can't pick your circuit up anymore. Your circuit can only be so small, and you still have to be able to pick it up. So for silicon, because it's been optimized for size, and all the transistors are very small, you can fit an awful lot of transistors in the smallest pick-upable size of silicon. So you can fit 10,000 transistors, or now 1 million transistors, in the smallest area you can pick up. But we're not talking about using 1 million transistors. We are talking about making lights flash, or sounds happen, or some kind of code passing to a reader. You don't need millions of transistors for that. You need hundreds, maybe thousands, low thousands of transistors. So there's no requirement to have this level of complexity. And because of that, you can take the same graph for our technology, where you're not operating on silicon and all of the materials costs are significantly lower and the inward capital investment required is significantly lower. And up until 1,000 transistors, we still have a 95% cost advantage relative to silicon, and most of the applications that we're looking at fall roughly within this area. Then, of course, it's the same. You've got a cost per area after that once you get beyond a certain area. And eventually, we become more expensive than silicon, above about 100,000 transistors. So that would make no sense to enter fields like that. Silicon is very well developed in all of that, and we're not aiming for that market at all. So an example, a case study here for HF RFID, because it's not just the circuit itself that has to be cheaper, the whole system has to be cheaper. So this is a summary of a tag cost breakdown for the whole tag. So the flex IC, the antenna, and the attach of the antenna. If you look at this image in the bottom left here, you'll see that just here, there's a flex IC that's bridging the antenna. And you do not need, therefore, a separate interconnects there to get across that gap. You can use the IC as the bridge. In a silicon industry, your IC is only 400 by 400 microns at this point. It can't get across that gap, or 400 square microns, I can never remember the number. Can't get across that gap, and you need more attached processing. And consequently, our cost of the whole solution is significantly lower than it would be in silicon, because some of the other peripheral costs are also lower. So if you can do this, and you can put this on all your shampoo bottles or all of your toothpaste or whatever, then you can get to the point where you can do item level tracking for your stock. So if you're a business and you want to know where all of your stuff is, then you can look in your warehouse and you'll be able to find it, and you'll be able to find exactly which one you've got, or on the shop floor, or if you want to have it for brand protection purposes. And it's relatively easy to then use it for anti-counterfeiting or wine labels and other applications. We have this banknote on our slide, which I don't like. The banknotes, I think, will be obsolete before we would want to use banknotes as a case for where we would go. But theoretically, you could. It is thin enough to go in a banknote. You wouldn't notice it was there. If it was sufficiently mature that it could do that, clearly that's also a very big business right now. But in 10 years' time, maybe not so much of a big business. So I guess the message that I'm trying to get across today is that to get to the outer boundary of the Internet of Things and really make everything at least partially smart, you really have to look at cost and form factor, and that the circuit needs to be as good as it needs to be to do its job. It doesn't have to be a motorway if you're just trying to drive a tractor through a field. It doesn't have to do all of those extra things if it doesn't need to. It's the cost and the form factor that are important. So our solution supports that, and in the next 12 months or so, we will have a manufacturing facility that is operational at making these in volume. So low cost does not necessarily mean low value or low margin. And then just to show at the end that we have tried to push ourselves in certain areas. This is a slide from a year or two ago where Mike Muller stood up at TechCon and showed a system on plastic, which is we've been working on with James and Andy and John Biggs, which is based around the Cortex M0 to really push the technology further. And that's what I wanted to say. So any questions?